Woit, and I teach in the mathematics department at Columbia University, where my title is Senior Lecturer. Yeah, well, the first thing to say is that when people talk about string theory, they're actually talking about a very complex set of ideas that lots of people, a very large number of people have worked on and done a lot of different things with. The probably what it's best known for and what got people all excited about it in the physics community is kind of the conjecture that instead of, at the most fundamental level, you can understand matter and the universe in terms not of point particles, which is the way our best theories currently kind of understand things, but in terms of kind of vibrating kind of loops of some elementary object. So your elementary object, instead of being a point-like thing, is something you should think of more as being a one-dimensional loop or a kind of string which is kind of moving around. So it has a lot more, it can do a lot more complicated things than a point, this kind of loop of elementary matter, or whatever it is. And so it gives you a very different kind of class of theories than the ones that we've been so successful with before. And so during the 60s, this idea was initially developed, and initially people tried to do one thing with these class of theories, something which didn't work out that well. And then starting in the late 70s and 80s, people then came up with the conjecture that maybe you really could unify all of physics and solve some of the open problems in physics by replacing our standard theory, something we call the standard model, with some kind of string theory. And that's so since this idea became very popular in 1984, and so it's been now 25 years, people have been working very hard on that. And I think just the initial thing that got people very excited, at least I would claim, really hasn't worked out and really can't work out. And that's kind of been, I think a lot of the recent controversy has been an argument over this issue of, whether this very speculative idea about whether you can use these strings to to get a unified theory, about whether that really is that an idea that's failed, or is there still some hope for it? I think that's really what's the controversial part of it. Well, the main thing to understand about the current state of physics is that we're in some sense kind of a victim of our own success. We have an incredibly successful theory called the standard model, and it really explains everything that we can observe about in terms of a fairly small number of elementary particles and some basic forces between them. And it's a quite beautiful theory, and it really is just kind of absurdly successful. Every experiment anybody knows how to do that in principle can be that this theory has something to say about, it works out perfectly, to whatever experimental in whatever detail you can do an experiment to whatever precision, it comes out exactly as predicted by this model. So we have kind of a semi-unified theory. We have this quite nice, beautiful structure which explains everything we can see, but it still leaves open several questions. And some of the questions are just kind of why, we have all these different particles, they all have different masses. Why do they all have different masses? We don't understand why the electron has a certain mass, quarks have other masses. So they're just kind of things which the theory just doesn't address. It just doesn't answer these questions, and they're questions which as physicists we think there should be answers to. But then there's also one kind of remaining force which isn't part of the standard model, which is the gravitational force. And the gravitational force is much weaker than these other forces, and it has a somewhat different nature. So the problem with it is that we don't these other forces, we have something which is a quantum theory. It's quantum mechanics. It really works down to the microscopic level, and in terms of this very fundamental idea about reality called quantum mechanics. The theory of gravity that we still use is Einstein's theory of general relativity, and it's what we call a classical theory. It's not a quantum mechanical theory. And you can make an estimate. The problem is that you can make an estimate within this theory of how big quantum mechanical effects would be, and that estimate tells you that they're just so absurdly small you can never hope to see them. So there's kind of a problem of principle. We have this theory which is not a proper quantum mechanical theory, and we know that there's things which it can't quite properly explain, but they're far too small for us to study them and to try to see them. So anyway, so we're not completely happy with this setup. We have a a force which doesn't quite fit with the others, and which for logical reasons we would like to unify it with these others and understand it as a quantum mechanical theory, and we've never quite been successful in able to do that. And this is what string theory was kind of a promise of a way of how to do that. And anyway, that's why people got so excited. It's kind of a famous phrase among physicists. It goes back to there's a well-known theorist called Wolfgang Pauli in the 50s. The story is that towards the end of his life, someone, I guess he was well known for being very kind of hypercritical of things that were going on, and would get up in the middle of a seminar and start saying, it's wrong, it's completely wrong. And late in his life, someone asked him about some work, some speculative idea of someone, and he evidently shook his head and said, well, that one's not even wrong. And so it's a well-known phrase among physicists, and it kind of carries, I think, two meanings. I mean, one of them is just kind of somewhat of a term of abuse. Well, that's so bad it's not even wrong. But there's a more interesting, and there's also a more kind of technical meaning that very often you have a speculative idea, and if it's not a very good idea, or it turns out you actually can't, you end up not being able to do very much with it. You end up not being able to predict anything with it, or it's just not useful. So there's also a notion of not even wrong, in the sense that it's not an idea which can be fully developed or can turn into something which is powerful enough to actually predict something and be wrong. So one problem with string theory is that it's kind of a theory which can explain what the problems are, but the problems are such that you can't ever even pin it down and say this is exactly what it predicts and let's go out and test it. So it's not even capable of being wrong or being falsified or being shown to be wrong. So that's the more relevant meaning here, really. As I said, I mean, string theory is actually a very complicated story. So if you start out with this hypothesis that maybe our fundamental objects are not points but are these strings, there's a lot of different things you can try and do with that. You have a whole different class of theories you can play with, and so I think if you look at what most people who are still doing string theory are doing, they're actually not directly trying to to develop this unified theory anymore. They're off kind of doing other things with string theory. People these days are trying to apply it to problems in nuclear physics. They're applying it to problems in solid-state physics, understanding superconductors. So the people who still are interested in it, are often kind of, even if they may or may not explicitly admit that they've kind of given up on the unified theory idea, but they're often doing other things. So there's a very active pursuit of string theory with other applications that don't have anything to do with unification. It's also turned out to be very interesting in mathematics. One of the things that I'm most interested in is the intersection between mathematics and physics, and the way the two fields kind of affect each other, and ideas from physics lead to very interesting things in mathematics. Ideas in mathematics get used and give us new physics. And string theory has been very, very fruitful in terms of raising questions which have led to very interesting mathematics. So there's a very active field of research kind of in between math and physics in string theory, but it just doesn't seem to be relevant to this question of unification. I certainly shouldn't. My criticism of string theory is not that, well, if you guys would just realize that you should be doing such and such, that would solve a lot of problems. I don't actually. I don't think that I have my own ideas which I'm very excited about, which I'm pursuing, which are also new ideas about how to use mathematics to do things in physics which don't have anything to do with string theory, and which kind of at least lead me to see there's a lot of areas, a lot of things we don't understand, which are closer to the standard model, which we do know works. There's a lot of kind of mathematical structure behind the standard model, which is still kind of mysterious and which is not well understood. And I think pursuing that is more likely to get us somewhere than the string theory unification idea. Just because you're starting from something which a theory which is right, and trying to further develop your understanding of that theory is maybe a more fruitful thing to do than trying to just kind of throw all that out and start afresh with something more speculative. I guess one thing to talk about is the this what's happening in Geneva even this month, and so a lot of the problem with the field, as I've said, is this business of being a victim of our own success, not having any experimental results that disagree with the theory, which makes it very, very hard to figure out how do you improve a theory if you've got no kind of clues as to what what might possibly be wrong about it, needs to be changed. And so there's this accelerator called the LHC, working at CERN in Geneva, and it's been in development for quite a few years now, and it's been a long process getting it working. But just over the past month, they've finally managed to inject beams into this accelerator and start colliding these beams and start doing some new physics. And over the next year, they'll start raising the energy of this accelerator to the point where we'll be in a new energy regime which allows us to get experimental data about what's happening at higher energy, which corresponds to what's happening at shorter and shorter distances. To see what's happening at shorter and shorter distances, in some sense, you need to use shorter and shorter wavelength or higher and higher energy probes. And this new accelerator, it finally promises some data in this new energy range beyond what we've been able to see so far. And there are reasons to believe that this new energy range is one where that we can actually start to get answers to some of these questions especially about mass, about why do different particles have different masses. So the state of the standard model is that it's this quite beautiful theory, but you to make the whole thing work, you need you need to make sure that a certain kind of physical phenomenon has to happen. And one way of saying it is that the theory has certain symmetries, and the lowest energy state, the vacuum of the theory, has to have non-trivial properties under one of these symmetries. It can't, normally you say a vacuum state is just kind of completely uninteresting. If you rotate it around, move it around, the vacuum state, nothing can happen, it's just a vacuum state. But the vacuum actually has to have interesting properties under these kind of mathematical symmetry transformations. And so we know that has to be true in order to make the theory work. And there are many ways you can imagine making that happen, and one way is called the Higgs mechanism. And so the Higgs mechanism involves postulating the existence of some new field, some new kind of matter, which is this Higgs this Higgs field, and then giving this the dynamics, or the making the properties of the Higgs field such that in the vacuum state the Higgs field will have this non-trivial property. So you can do that. In some sense, the Higgs field is kind of the simplest way of getting what you want. But when you do it, you also you end up losing the ability to predict all sorts of things, because then the question of why does a particle have a certain mass just becomes, well, because that's how strongly it interacts with the Higgs field. So it's the simplest way of making something happen has to happen, but it's a way which has a lot of things you don't really like. It's not a very satisfactory way of doing it, because it kind of necessity then leaves open a whole range of questions which you would hope to have answers to, but you just can't answer that way. So one thing which we hope to learn from the LHC is this Higgs mechanism, or is this Higgs field really there? In which case, that'll be actually somewhat of a disappointment, because it'll mean that, okay, this theory kind of continues to work, and we still don't know how to answer some of these questions. Or I think that the much more exciting possibility is going to be that there's something else causing this phenomenon of the vacuum behaving this way, and this something else would be give us would be something which would be more interesting and would allow answers to these questions. So this name of the Higgs field and finding the Higgs particle, that's kind of it's an oversimplified way of saying what we're really hoping, which is we're really hoping to understand what is causing the vacuum to behave this way, and we have good reason. There's kind of a number in the theory which kind of says how big this phenomenon going on in the vacuum is, and what the size of it is. and the size is exactly the size that this accelerator should finally be able to probe. So it's not. There's a very good reason to believe that this is the right machine to kind of to start answering some of these questions. The real problem is that the ways that there are various ways. A lot of people have studied a lot of other alternatives to the Higgs field, which the problem is that they're all fairly complicated, and none of them, they all have as bad or even worse problems than the Higgs field. So they've all, so none of them are convincing. We don't have a convincing alternative to it, and I don't either. I guess, I mean, the one, about all I can say about that is that I'm very interested in some of the kind of mathematical parts of the theory that we don't understand, and some of the kind of deep mathematical structure that we don't understand in these theories. And part of what we don't understand in these theories actually is, is related to this problem of the vacuum, of this behavior of the vacuum. So, I mean, in my ideal world, it would turn out that there's something there's something still to be learned about the mathematical structure of these theories, which would in the end explain this Higgs phenomenon, this problem with the vacuum. But I mean, I wish I knew how to do that. But I certainly don't have some very vague reasons to believe that that's an interesting thing to look at. But I certainly don't have an answer to it. And I think if I had to assign probabilities to it, what I would guess is that I'd say there's about a 50% chance the LHC will actually see an actual Higgs particle, and there is some kind of Higgs field, and that this is going to be kind of depressing for us because it means, well, whatever, there is this field there, it's working like this, and these questions that we would like answers to you'd have to go to even higher energies or smaller distances to understand them. Or I think there's a 50% probability we'll find that we won't see a Higgs particle, or at least not a Higgs particle of the kind that you see in the simplest model, and that will actually give us clues as to what's really going on, and that will be much more exciting. So, but I don't know which is going to happen. You never know. I mean, there's no reason to. The general problem with particle physics is that these questions we're asking are at they're happening at such high energy scales or such short distances that it's very hard to see how to do anything very practical with this. I mean, anything like these particles we're talking about, often have lifetimes which are 10 to the minus 20 seconds, or I mean they're just, if you produce a Higgs particle, it's going to be so short-lived. It's incredibly difficult to even see any evidence of the thing. It's not something you're going to be able to go out and use these Higgs particles to carry around and do something with. On the other hand, you don't really know what you're going to find. If you do find, especially if you find something, I guess I could say it this way: if you do just find this Higgs particle and just this Higgs field, it's very hard to do anything really practical with that. If you find some completely new understanding of this theory, then who knows? I mean, you can conjecturally come up with all sorts of models. You can come up with models in which there's kind of new, heavy, long-lived particles, which you could then imagine doing things with. But I think it is probably a pretty good bet that within the near future, this is not really particularly practical. This is really a matter of just trying to understand the world better, not in a way that's particularly going to be useful for doing anything too practical. It's going to affect people anytime soon. I mean, some of that is because people. One of the alternatives to this Higgs mechanism is that, and people started studying some models in which, well, to go back a little bit, I mean, one thing about string theory is to make string theory work, you have to have extra dimensions. You have to have more than the 3 space and 1 time dimensions, and that's kind of in some sense the main problem with string theory, that you have to have like at least 5 extra dimensions. Sorry, 6 extra dimensions, and the predictions of theory and being able to use it for anything depend on what's happening with these 6 extra dimensions, and no one has ever. Initially, the hope was that there was a fairly small number of consistent ways of dealing with these extra dimensions, and that would make this a predictive theory. But it's turned out there's just too much you can do, and you can kind of get anything you want by having these extra dimensions do different things. And so one thing, as part of this, one thing that people studied was models in which these extra dimensions are actually of exactly the right size that the LHC should start seeing evidence of these extra dimensions and producing black holes because of these extra dimensions. And that's there's just never really been a reason to believe that these extra dimensions we'd see no evidence of them at our best accelerators now, and we'd go up by a factor of 7 in energy, and all of a sudden all these extra dimensions would appear. There's absolutely no reason for that to happen. You can make speculative models in which it happens, but there, first of all, anyway, so there's really kind of no good motivation for these models, and for them to happen, and no evidence for them. And then even if they were to exist and they did happen, any such black holes would kind of immediately they'd be kind of completely unstable and would just immediately decay into something else. So you're not going to produce a dangerous black hole that way. But the first kind of, I think what caused all this trouble is that people kind of wanted to promote these extra dimensional models, even though there was no good motivation for them. And so they promoted them by saying, well, in principle, since we don't know what happens at higher energies of the LHC, maybe evidence these extra dimensions will show up, but there's no good reason for that. But once people started promoting the idea these extra dimensions might show up, then people said, well, if they show up, then maybe there'll be black holes. And it was kind of speculation on top of speculation on top of speculation. But it's all stuff which has no reason to believe that any such thing could possibly be true. I mean, the thing that most fascinates me about this whole subject is something that the problem is it quickly gets very technical. But there's an area of mathematics which is known as representation theory, and one way of thinking about it is in terms of what physicists will often call symmetries. So for instance, one of the basic facts about the laws of nature is that they're symmetric. Laws of nature are the same at if you move in any direction, or you move in time back and forth, the laws of physics don't change. If you rotate things around in 3 dimensions, laws of physics don't change. And so there are these so-called symmetries, and these symmetries have very important physical implications. So for instance, the fact that the laws of physics don't change as if you move in time has a physical implication that there's this thing called energy, and energy is conserved. And same thing, the fact that laws of physics don't change if you move back and forth in different directions in space implies that there's something called momentum, and momentum is conserved and doesn't change as you evolve in time. And so these very, very fundamental facts about physics are kind of deeply grounded in the symmetries of nature. And so to a mathematician, this question is a question about what we call about groups and representations of these groups. So if you go into any math department and look at what they're doing, you'll see that that a lot of people in different kinds of mathematics are studying different structures which are all so-called groups, and they're often studying what are called representations of these groups. So even people studying number theory, kind of abstract things about prime numbers or something, they're also studying groups and certain representations of these groups. So there's kind of to the extent that mathematics has a kind of unifying theme and a unifying principle which shows up in different areas of mathematics, it's about these representations and representation theory. And the thing that one of the things that most strikes me about physics and most fascinates me about it is that if you look at quantum mechanics initially looks like a very odd structure. It's not something we have any kind of intuitive understanding of. It doesn't look like, like what the way we're used to thinking about physics based on our everyday experience. But if you look at the mathematical structure and the basic structures of quantum mechanics, they're exactly the structures that show up in this theory of representations. So there's a kind of a deep relation between math and physics, which is surrounding this whole notion of symmetries and representations of symmetries. So that's one thing that's always fascinated me, and my own research, my own interest is in kind of developing, taking a lot that's been learned in mathematics. There's a lot that's been learned in mathematics over the years about how to think about representations and how to construct them and how to work with them. Some of it has made its way into physics and been used in physics and was been used in physics since the early days of quantum mechanics. And so, for instance, one of the great kind of, to the extent there's a kind of hero of this book I wrote about this, it's a mathematician called Hermann Weyl, who kind of was one of the first people to understand how quantum mechanics worked and to understand the relation to representations. But anyway, I think there's still a lot to be learned in that way, and very specifically, the so-called standard model has this group of symmetries which is called a gauge symmetry, and it's an infinite-dimensional group, and the standard kind of physics conjecture or understanding of the representations of this group is that that should not be an interesting question, that there should only be a trivial representation of this group. But anyway, my conjecture is that there's actually a much more interesting question there, and pursuing that, pursuing this question of how do you deal with the gauge symmetry of this theory in terms of using ideas from representation theory that are more well known in mathematics, that haven't been used in physics before, that you can actually get somewhere. So that may be a bit too technical, but that's about as good as I can do with this. So it's hard to say, and there's we'll get proof. I don't know. There's a lot of, I mean, the problem with elegance is actually, it's an interesting question maybe to say what is elegance and what is beauty, I guess. So one thing that's come up even within the string theory issue is this question of, is this a beautiful idea or a beautiful theory? So my colleague Brian Greene has wrote a very, very good book about this called The Elegant Universe, and so he's and within physics, this is our, I mean, we're often very struck by some of these basic ideas are we like to are very striking, and we like to in a way which we like to describe as being elegant or beautiful. But the problem with that terminology, especially with the terminology of beauty, is that beauty means a lot of different things to a lot of different people, a lot of different ways in which things can be beautiful. But this really has a very specific meaning, and which is more along the lines of elegance, which is that we say that an idea is beautiful or elegant in mathematics or physics if a very simple principle or a very simple idea or a very simple set of ideas turns out to be very powerful and leads to all sorts of unexpected structure and unexpected predictions. And I think maybe what I find is the most beautiful, most elegant thing about this whole subject is a little bit what I was trying to explain earlier. For instance, this idea, maybe just to say this idea that the fact that the laws of physics are the same as you move in time means that has very unexpected significance. It means that there is this thing called energy, and you can associate a number called energy to physical systems, and it's not going to change as time evolves. So I mean that's actually the so in classical physics, that's actually that's a theorem called Noether's theorem, after a mathematician called Emmy Noether. So there it's a little bit of a slightly non-trivial theorem, and that's certainly a beautiful theorem. What fascinates me more is that in quantum mechanics, Noether's theorem isn't even a theorem. It's just implicit in the definition. Just the way you set things up, it just is automatically true. So it's anyway, there's the theorem and a proof in classical physics, and then you start thinking about quantum mechanics, and you think about it, and then it's just kind of automatically true. There's not even a theorem anymore, and that's just beautiful. Well, I think any kind of thing that human beings do, there's certain politics to it, and certain academic politics and politics within fields. So, but mathematics is actually a relatively healthy field these days. I mean, people are making good progress in a lot of different ways, and it's also so anyway. I've kind of lived part of my professional life in mathematics and part in physics, and one thing to say about mathematics is it can have its problems, but it's actually hasn't seen. It hasn't seen a lot of the problems of other sciences, and politically, partly also the wonderful thing about mathematics is since so much of it, what people are doing is completely useless. Nobody, nobody kind of in the outside world really cares very much. You don't have kind of a right and left and people getting in, kind of ideology coming in because there isn't any. It just doesn't actually connect up to the kinds of things that people who worry about ideologically worry about. So in most of mathematics, it just doesn't tell you anything one way or another about global warming or about healthcare or about any other number of things you might care about. So mathematics is immune to a lot of exterior real world politics because of that. And the academic politics it's there, but I think it's actually less than a lot of fields. One of my colleagues likes to say that mathematics is he thinks that about the only subject that he knows of it in academia or in the real world where if two people disagree about something, if people are studying some mathematical object and there's supposed to be a proof and they disagree about whether this proof works or not, they will go into a room, sit down, and talk about it, and fairly quickly or at the end of the day, one of them will admit they're wrong. And he says, that's the problem with a lot of subjects. This just doesn't happen. Whereas in mathematics, this just happens all the time. And so people, there is this notion of logic and proof and rigor, which we can all allows us to kind of all stay on one track. Physics is the thing I say about physics. First of all, physics is a very complicated subject with many different things. So string theory and particle physics are only a small part of physics. So when I talk about physics and I talk about them and the problems of those subjects, it's really problems of a very small, one discipline and one subfield of physics. And a lot of physicists, people are kind of happily going on and doing their science and quite successfully, and it has nothing to do with, and they get very annoyed when they hear people going on about the problems of string theory as if that's some big problem for physics because it's not their problem. String theory and particle physics, it suffers, I think, a lot from this business of being from its own success, from not having any, nobody kind of has been able to come up with any really good ideas to make positive progress, just because there's been no experimental evidence to give you a clue as to which direction to go, and that the subject has, I think, traditionally been very conducted, often in at least from a mathematician's point of view, in a very faddish way. That everybody, all the smart people in the subject, the idea was it would all kind of jump at the same problem and all try and work in the same problem, very often because the subject was driven by experiment. And somebody would go out and turn on a new accelerator like the LHC at higher energy, and this is certainly going to happen next year if the LHC sees something unexpected. Everyone in the whole field is going to be trying to explain that one thing. And so you have a little bit of kind of faddish sociology that everybody is trying to do the same thing at the same time, whereas in other fields like mathematics, people kind of spread out and develop their expertise and work on different things. So part of the problem of the politics of particle theory has been that you have people used to the idea that, well, you should look around and see what these smart people are working on, and I should work on the same thing as them. And so you have all these people kind of trying to do this, and so string theory then got identified back in '84 as being the hot topic, and for a lot of reasons, partly because it was an intriguing idea, but partly also because there's one of the great geniuses of our subject, this guy called Edward Witten, who's just fantastic genius who's done these amazing things, and he got very interested in it, and he started promoting the idea that this is a very promising idea, and so everyone kind of jumped on it, and my initial reaction at that time, I was just getting out of graduate school at that time, and my partly the way I work and the way I think, I wasn't so interested in the idea of trying to do the same thing as everybody else. I would prefer to work on something a bit different, and partly also it didn't seem to me that it wasn't that this was obviously a good idea. It might be a good idea, might not, but there were obvious problems with it from the beginning. And so anyway, so starting in 1984, everybody started working on this, and I think my reaction to it was, well, that's great that they're doing this, and what's going to happen is what normally happens in the subject is that after 6 months or a year or 2 years, people will see whether it's a good idea or not, and and if it's not a good idea, they'll move on. And the really peculiar thing that happened here was that 25 years later, this is still there's still a lot of people doing this. I mean, it really kind of caught fire, and even without succeeding, it still kind of developed into this huge subject, and it kind of, in some sense, kind of achieved some kind of critical mass. That more and more people were working on it, and they're working on it for so long that people ended up kind of devoting their careers to it. And it's a very, very difficult and a very complicated subject, and it requires quite a lot of time just to even get to the point of understanding what's going on. So you had lots of more and more people working on this, investing more and more of their time and their careers and their lives into it, and I think it really got to the unfortunate point that people were kind of unwilling to kind of admit that this wasn't working. And it's a natural human reaction to an idea if you're fond of it, you put a lot into it. It's kind of hard to get you to admit often, well, maybe this doesn't work. And this is kind of happening very much in spades in this story. I think it's been very hard to get people to kind of admit that this is something that hasn't worked out. So there's actually kind of two. There are kind of two things. One is the blog. I also wrote this book, and so the anyway, for many years I wasn't very happy with what was going on there, and I was kind of observing that, okay, this is becoming more and more problematic. There's this, not only are people kind of not admitting that this isn't working out, but there's this whole, there's a lot of kind of public promotion of the subject, and it's a very difficult, complicated subject. A lot of people don't understand it, and so this is really not a healthy situation. So someone should kind of clearly explain to larger community of physicists and also to non-physicists, exactly what the situation is here. And so I wrote an article about this, and then I finally wrote this book, and it took a while to get the book published. That's a long and interesting story. But then after the book was written, I also started to see there were a couple other physicists who had started blogs, and I thought, well, this is an interesting thing to try to do, and I can both talk about these issues related to string theory and things which I was trying to get at through the book, but also kind of follow it on a day-to-day basis, and also just kind of write about whatever I'm interested in. So the blog, I guess I don't worry a lot about the audience for it. It's kind of written. I guess I realize it's really just kind of whatever I would like to read. So I'm kind of writing whatever I would like to read. So if there's somebody out there exactly like me, they must find this really fascinating, and if there's something quite different, they find it not at all interesting. And so, because of that, it's the kinds of things on the blog are often, if I learn something, there's something new, interesting going on, and even in pure mathematics, I'll be writing about that, or pretty much anything going on in between mathematics and physics, I'll be writing about that. I'm writing a lot about the LHC, and also just about whatever is going on in this controversy over string theory, and it's kind of. It's interesting that more kind of keeps happening with that. My book came out, and at the same time there was a book by another physicist with a similar point of view to mine, and all came out. So that caused a lot of controversy. So there's a lot of reviews and a lot of argument going on these blogs, and a lot of people refer to this as the string wars. And so there's this for I don't know, a year or two there was a kind of very interesting. If you're interested in this kind of thing, there's an interesting warfare in terms of blog postings and comments going on my site and various others, and that would lead to all sorts of strange things. I don't mean it depends. I often learn interesting things from comment. So now that the blog is fairly well known, so people will write in comments on my blog, often telling me about something I hadn't heard about or know about, and that's very interesting. Or they'll often send it to me privately by email, saying, hey, you might be interested in this, and so I get a lot of that. I learn a lot that way. One interesting thing I found amusing about the whole string theory discussion was that it's it really is. It's an incredibly complex and difficult subject, and so it's really hard to overemphasize how it's a subject that really nobody understands very well, and even the people who are the most experts at it are. I had this amazing experience of having a conversation with some Nobel Prize winners who people are thought of as the brightest people in this field, and asking them what they think of string theory, and they'll say, I don't know, I don't really understand what's going on, I don't want to comment on it, and it's just, I'm baffled by it. So one interesting thing about the some of these discussions in the blog was I found one way to figure out exactly what's going on in string theory and whether something is really a problem or not is to just put up my understanding of it, in a blog posting or in a comment or whatever, and then fairly quickly you would find that either I was wrong and there was some reason that this actually made sense even though I thought it didn't, and I would quickly, often abusively, be explaining to me what an idiot I was and why this was, here's the answer, what you really should have known, and then I found out that, okay, I learned something, or often I would find out that if I was right, if there really was a problem here, the answer I would get would often be just this abuse of, oh, you're a complete jerk and you're a moron, but no scientific answer to the scientific question. So that was actually an interesting way to kind of see exactly what the state of research in the subject was by kind of probing it and trying to and getting that kind of response from some of the more hostile people in the subject. I mean, it's mostly a positive thing. I mean, one thing to say about one of the main problems with the blogs, one of the most annoying thing about the blogs is, especially if a lot of people are reading it, you're really in a situation where there's a small number of people who really understand this and know what's going on and have something really sensible to say about it. There's a very large number of people who have some kind of interest in it and have the time and energy to sit there and write uninformed things on your blog and kind of just so I actually did. I think unlike some blogs, I actually delete a lot of the comments submitted to my blog and try to keep the noise level down. And so that's probably the most discouraging thing about the whole experience. It's just the number of people out there who kind of want to go on about this and argue about this, but don't know what they're talking about, and want to kind of fill the internet and all information sources they get their hands on with kind of uninformed nonsense. So there's a lot of that, but but just the kind of discussion of the subject and of its problems, which I think went on in these blogs, and which if you're interested, you can now have information go and see and read. I don't think there's really any other form. It's an amazing format for that. There's really no other way that that discussion could be held in that way, and also, I mean, the internet just provides this kind of amazing access to information of a sort, which is just totally unlike anything we've had before. You can just Google some term and immediately have access to all sorts of often high-level discussions of this subject. And I think it's actually made some of the faddishness of particle theory actually a bit worse, in the sense that one thing that used to kind of slow down fads was just how long it took to communicate them to people. I mean, the certain prominent people might have started working on some idea at Princeton or Harvard, but it would take a while for that news of that and understanding of what these people were doing to filter out to the rest of the community. And if people wanted to kind of jump on it and pursue it in a faddish way, it would take them a while to even find out about it. Whereas now, everybody's kind of, every night there's kind of a new set of preprints coming out on the preprint server, and people logging in and looking at these, and the minute that somebody has some new thing which is becoming a kind of faddish thing to work on, everybody throughout the world has it at exactly the same time on their desktop and can start thinking about it and working on it. And so it kind of makes that even more so than it used to be.